Welcome to this explainer. Let's just jump right in, because today we're tackling a massive and practically invisible problem hiding inside almost every single piece of advanced technology you use. We're talking about the problem of extreme heat in modern electronics. As our devices get more powerful, they generate a staggering amount of thermal energy, and dealing with that heat, well, that requires a true superhero of material science. So today, we're taking a close look at a really fascinating material called aluminum nitride.
And it's a serious question, right? Just think about the world around us right now. How do we prevent electric vehicle inverters or massive AI data centers or even high-frequency 5G towers from literally melting themselves down? When you're pushing hundreds of amps of current through these densely packed semiconductor chips, traditional cooling just doesn't cut it anymore. You need a foundation, a substrate, that can pull that heat away instantly without causing a short circuit.
Which brings us to this absolutely staggering number: 320 watts per meter Kelvin. That right there is the theoretical maximum thermal conductivity of a perfect single crystal of aluminum nitride. To put that into perspective for you, standard low-cost ceramics usually hover around like 20 to 30. So this massive metric, it's exactly what makes aluminum nitride the ultimate heat-moving champion of the ceramic world. All right, Section 1. Meet aluminum nitride, the thermal champion. The unique superpower of this material is that it combines two things you almost never see together in nature. Usually, if a material conducts heat well, think of metals like copper or aluminum, it also conducts electricity. But aluminum nitride combines high thermal conductivity with excellent electrical insulation. It can yank intense heat right away from a microchip while keeping that high-voltage electrical current completely isolated.
But, every superhero has a kryptonite. That brings us to Section 2, the fatal flaw, subtitled Oxygen Defect Chemistry. Taking this stuff from a theoretical crystal to a manufactured industrial part is honestly a grueling hero's journey. Why? Because aluminum nitride has a chemical enemy that will absolutely destroy its thermal performance if we aren't incredibly careful. To really get this flaw, we gotta look at how heat actually moves through this stuff. It's all about something called a phonon. Unlike metals, which use a whole sea of free electrons to carry heat, aluminum nitride is a ceramic. It relies on phonons, which are basically these microscopic waves of crystal lattice vibration to transport heat. Imagine heat essentially surfing on high-speed vibrations, moving flawlessly through a perfectly ordered atomic grid.
But here's the catch. During the manufacturing of the raw powder, oxygen impurities from the air or even just moisture kind of sneak in. And this is the crucial chemical reality. For every 3 oxygen atoms that manage to substitute their way into the nitrogen spots of the lattice, the crystal is forced to create 1 aluminum vacancy just to keep its electrical charge neutral. These missing aluminum atoms, these vacancies, they act like massive potholes in our perfect crystal grid. When those high-speed heat phonons hit a vacancy, they scatter. They just crash.
You can really see the real-world consequences of those oxygen potholes right here. A pure single crystal sits at that theoretical 320 watts per meter Kelvin. A really good industrial ceramic hits about 180, which, by the way, is still fantastic for electronics. But if you have high oxygen contamination in your starting powder, your thermal conductivity completely plummets to 80 or sometimes even lower. Literally, just a tiny bit of oxygen ruins the exact reason we're using this expensive material in the first place.
So how do we fight back? Let's move to Section 3, the trial by fire, looking at the processing science. We have to figure out a way to bake this ceramic powder into a solid, dense block without letting oxygen ruin the whole thing. Which leads us to a massive manufacturing headache. Why is aluminum nitride so incredibly hard to bake or sinter? Why can't we just press the powder into a shape and toss it in an oven? Well, it's because of its strong covalent bonds. The atoms are holding on to each other so tightly that they absolutely refuse to diffuse and merge together. Plus, every single particle is naturally covered in this thin skin of surface oxide that physically blocks them from touching. If you just heat pure aluminum nitride, it doesn't densify, it literally just sits there until it gets so hot it decomposes. No good.
To get around this, scientists use a hero additive, yttrium oxide. It basically acts as a magical glue during the baking process. When you mix yttrium oxide into the raw powder and crank up the heat, it chemically reacts with that stubborn surface oxygen on the particles. It literally pulls the enemy oxygen right out of the aluminum nitride lattice and traps it into these secondary aluminate phases. So it cleans the crystal while simultaneously creating a liquid that helps glue the whole thing together. It's brilliant.
We call this intense, high-temperature process liquid phase sintering, and it happens in 3 distinct steps. First, as the yttrium oxide melts with the surface oxides, this newly formed liquid wets the rigid particles, physically pulling and rearranging them closer together. Second, the sharp edges of the particles actually dissolve into the liquid and reprecipitate, which shrinks the empty spaces or pores between them. Finally, in step 3, the closed pores are totally eliminated. Boom, you achieve a fully dense, solid ceramic. But hold on, the battle is definitely not over just because the heating stops. How you cool it down is absolutely crucial. If you cool the ceramic slowly, that trapped oxygen liquid actually has time to pull back into isolated little pockets. This allows the clean aluminum nitride grains to directly touch each other, creating a high-speed highlight for our heat phonons. But if you cool it too fast, that liquid freezes into a continuous glassy film right between the grains. You've just built a thermal wall, so even if your density is completely perfect, a fast cool gives you terrible thermal conductivity.
Okay, so we've successfully baked it. Let's step out of the furnace and into the real world. Section 4, the ceramic showdown. Let's pit aluminum nitride against its biggest industrial rivals, see how it survives, and check out its reliability.
Let's look at the tail of the tape here. Alumina is your cheap, abundant standard. Costs practically nothing, but its thermal conductivity is a measly 25. Then you've got silicon nitride, which is incredibly tough mechanically, but its heat transport only maxes out around 90. And then there's our champion, aluminum nitride. It totally crushes the competition in thermal conductivity at 180. But look at the trade-offs. It's super expensive to make, and its mechanical toughness is low. It's strong for sure, but it is very, very brittle.
Which brings up a really fascinating engineering concept, perfectly captured by this quote. Ceramics don't have one strength. They have a distribution of strengths. Engineers call this Weibull reliability. Because aluminum nitride is so brittle, its failure is entirely dictated by microscopic flaws. Literally, a single invisible crack introduced while diamond grinding the edges can cause a high-voltage substrate to catastrophically shatter under thermal stress. So you aren't just buying the material, you're paying for the absolute perfection of its processing.
And speaking of flaws, let me let you in on a very surprising weakness of this super material. Despite being this rock-hard ceramic, simple water is its absolute worst enemy. Through a chemical process called hydrolysis, if aluminum nitride is exposed to moisture, it reacts to form aluminum hydroxide and ammonia gas. The water literally dissolves the surface of the ceramic over time, totally destroying its thermal and electrical properties. If you're building a water-cooled heat spreader, you have to carefully protect or coat this ceramic, or it's game over.
So, let's recap. It's brittle, it hates water, and it's incredibly difficult to bake. But its thermal superpowers make it absolutely essential. Let's move to our final section, Powering the Future, to see exactly where this high-maintenance, ultra-powerful material actually lives today.
Now, a bare piece of ceramic doesn't do much good in an electronic circuit. We have to figure out how to attach metal to it. The older, mature technology is direct bond copper, or DBC. But for extreme performance, we rely on active metal brazing, or AMB. This uses reactive metals, like titanium, to chemically bite right into the ceramic, creating a wildly strong bond. This AMB technology on an aluminum nitride substrate is the exact reason your electric vehicle can fast charge in 20 minutes. It handles the extreme thermal cycling of the EV's inverter without ripping itself apart or melting.
Beginning to that finish part, yeah, not cheap. If you look at the manufacturing cost for premium aluminum nitride, sintering at extreme temperatures takes up 30% of the cost. The ultra-pure raw powder, that's another 25%. Metallization takes 15%. But notice that machining takes a massive 30% of the cost. Diamond grinding a brittle material perfectly flat, without introducing any of those catastrophic Weibull cracks we talked about earlier, drives the price up enormously. You are paying a premium for extreme precision. And that precision is basically unlocking the future. Aluminum nitride is the hidden backbone of our next-generation technology. It's in EV power inverters and AI data center heat spreaders as a bulk ceramic. It's used in semiconductor fabs because it resists the harsh plasma used to etch microchips. And, amazingly, as a microscopic thin film, it's piezoelectric, meaning it's used in the 5G RF acoustic filters right there in your smartphone. When doped with scandium, it becomes an incredibly powerful MEMS sensor material. I mean, it is truly a dual-threat material. So, from a heavily flawed, oxygen-contaminated powder fighting through the extreme trials of liquid-phase sintering, aluminum nitride emerges as the thermal savior of the modern electronics industry. It's just a phenomenal story of defect chemistry and processing science. But I think it leaves us with a really provocative thought. As our technology continues to get smaller, faster, and much, much hotter, what other supermaterials are hiding out there in the periodic table just waiting for us to figure out how to bake them? Keep that in mind next time you fast charge your devices. Thanks for exploring this with me.